Alright, welcome. In this video, we're going to be talking about the tangent function, the graph of y equals tangent x, and also a little bit about period and frequency, because, we never talked to you about that, but that's something we do need to tell you about. As you can see, it's one of our essential knowledges. So the first thing I wanted to say is, okay, period and frequency. Okay, the period and frequency are reciprocals. If the period of a function is p, then its frequency is 1 over p, and that's what it means to be reciprocals. Okay, so I'm just going to kind of show you what I mean with some examples. All right, so for this first example, we've got a wheel rotating at a constant rate, and it's going to complete 12 rotations every 3 minutes, and it's going to ask us what is the frequency, indicate units of measure. Well, that's kind of new. We don't even know what the units of frequency are, so what we should do is stick to what we're familiar with, which is period, and we just take the reciprocal. So I'm going to remind you that when we're looking for the period in like an applied context, the period is how long it takes to complete one full cycle. So we can compute that by, giving the amount of time they give us and dividing by the number of cycles. And that's what we've got right here. We've got 12 rotations every 3 minutes. So 3 minutes, that's a measure of time, and 12 rotations. So I'm going to say P equals 3 minutes divided by 12 rotations. If I were to simplify that, 3 over 4, so 3 over 12 is 1 over 4. So I'm going to say that's 1/4. But the units, rather than saying minutes divided by rotations, I'm going to say minutes per rotation. And then if I want to find the frequency, well, I've got this brand new formula. Frequency is 1 over the period. And I'm afraid face might cover this workup, which is going to be 1 over a quarter, which is going to be 4. And the units of frequency, if the units of the period are going to be minutes per rotation, units of frequency will be rotations per minute. So that would be 4 rotations per minute. That makes a lot of sense. If it completes 12 rotations every 3 minutes, it's averaging 4 rotations per minute, and it's going at a constant rate, so it is actually doing 4 rotations each minute. And so here, if we've got a dog breathing at a constant rate, breathing 3 breaths every 2 seconds, and you're asked about the period, okay, well, that's why I'm going to start with period, right? And I probably should have put this example above the other one, but it's all right. It's fine now. Remember, period is time divided by the number of cycles. So the time is 2 seconds, number of cycles is 3 breaths. So I'm going to say period is 2 breaths divided by 3 seconds. And the only thing I can do to simplify that, 2 over 3 is 2/3. And so I'm going to say 2/3 of a second per breath. Okay, 2/3 seconds per breath. That seems like that might be reasonable, especially if the dog's panting, breathes pretty fast. And then we're going to have a satellite orbiting a moon. It completes 1 trip around the moon every 13 hours. What are the period and frequency? Indicate units of measure. You try this one on your own. You're ready. Okay, you've seen me do the period. You've seen me do the frequency. I'd say go figure those out and check your work against mine. Do it with video pause, because I'm going to bring in the answers in just a couple of seconds here. All right, there you have it. So period, again, starting with time divided by number of cycles. Okay, the time was 13 hours, and the number of cycles was 1 trip around the moon. So it's 13 hours per trip around the moon. Around the moon is the period of the situation. And the frequency is 1 over the period, so it's 1 over 13. And that represents the number of trips around the moon I make each hour. Okay, so you can see that sometimes period is more of a useful way of talking about it, and sometimes frequency is. I think that's the message here. But we need to know the reciprocals. Okay, now with that out of the way, we're ready to do what we came here to do. Graph y equals tangent x. So we're going to start by sketching the graph of y equals tangent x on the interval -pi/2 to 2 pi. Okay, and so that's kind of a strange interval, and I think I've got a reason why. I'm not totally remembering why now, but we're going to start with the idea of the unit circle, and I'm going to fill in some values of x that we're going to want to find tangent of x at. All right, so I have put in the unit circle and, put -pi/2, -pi/4, 0, basically at intervals of pi/4 is what I'm interested in. And I've labeled all these points that I'm going to be talking about here in red. Okay, so I'm going to start at tangent of 0. Okay, remember that tangent is the y-coordinate divided by the x-coordinate on the unit circle, and at theta equals 0, that far right edge, the x-coordinate's 1 and the y is 0. So y divided by x is 0 over 1. It's going to be 0. Okay, at pi/4, cosine is √2 over 2, sine is √2 over 2. X and y on the unit circle are going to have the same coordinate. So you take the same number and divide it by itself, we're going to get 1. Okay, at pi/2, that's going to be the point where x is 0 and y is 1. So y divided by x goes 1 over 0. And we saw that a little bit at the end of the last unit, where tangent could be undefined, and pi/2 is one of those places. So I'm going to say just d and e there. It does not exist. Okay, then at 3pi/4, okay, the x-coordinate is negative, but the y-coordinate's positive. But we're still sitting on a 45, 45, 90 triangle where the legs have the same overall length. So tangent would be y over x is going to be a number divided by the negative version of itself. It's going to be -1. And then at pi, I'm kind of back to the same situation that I ran into at x equals 0, where y is 0, but x is not 0, so 0 over not 0, that's going to equal 0. Okay. Now I've also got these other 2 points where x is negative. And I don't think that's too hard for you to think about, like especially negative pi over 4 and negative pi over 2. If you know where regular pi over 4 and regular pi over 2 are, and you know where 0 is, it's going the opposite direction. So at negative pi over 4, I'm going to be down there where x is positive and y is negative. But it's still like root 2 over 2 and negative root 2 over 2. So if I take the negative version of a number and I divide it by the positive version of itself, I'm going to get negative 1. That's where I'd put in negative 1 there. And then at negative pi over 2, just like regular pi over 2, I'm dividing by 0 because cosine of negative pi over 2 is 0. Because the x-coordinate on the unit circle at that very bottom edge is going to be 0. So I'm going to say that one fails to exist as well. And so we see this repeating pattern here. D and E, negative 1, 0, 1. D and E, negative 1, 0. So we would expect the pattern to continue going. Right. Now, if the pattern was just to continue going, we would increase by pi over 4, and we'd go from pi to 5 pi over 4, and we would see that 1, because negative 1, 0, 1, D and E every time. And so I'm just going to confirm that with a little bit of unit circle trig work off there. We're going to just, draw 5 pi over 4 and figure out what tangent's going to be. It's going to be the negative root 2 over 2 divided by negative root 2 over 2, and that is definitely 1. So this is making sense to me. So now it's time to make the graph. Right, so I'm going to label my axes, because I didn't need that x over there. Just decide where x equals 0 is going to be. I know I need a little bit of places where x is negative, so I'm going to make it the far left edge, but I probably don't need to make it the exact center either, because then I won't be using the whole thing. Okay, now I think what I want to point out to you right now is these places where tangent fails to exist, right here and there. And we would think that at 3 pi over 2, we'd see the same thing, but that makes a lot of sense, because 3 pi over 2 is very similar to negative pi over 2. It's exactly the same in terms of its location on the circle. Okay, so we would see that a bit later. But what I'm saying is these places where the function fails to exist, it's failing to exist because of division by 0, right? Because tangent is sine over cosine. I realize I've never written that down in this video, and I think that's going to be good. That's kind of like essential to our understanding of the tangent function, in my opinion. And so it's division by 0 because of cosine equaling 0 at pi over 2 and negative pi over 2 and also 3 pi over 2 and places like that. And so division by 0, that's going to cause a vertical asymptote. That's what I'm saying. So we're going to have a vertical asymptote at x equals pi over 2 and at x equals negative pi over 2. Right, so I'm going to start with those. I'm going to put my vertical asymptotes right there at negative pi over 2 and pi over 2. And then from there, I'm kind of just going to fill in the points that I already know. Right, when x is 0, the output is 0. At negative pi over 4, which would be halfway to negative pi over 2, at least from 0, I'm going to be at negative 1. And I don't really know where that is, but I'm just going to decide negative 1 is right there. So that would make positive 1 about there. And so what we're going to do is we're going to respect these vertical asymptotes, kind of like we did when we were doing the rational functions, and go through all the points. So that means that I'm going to have to come from below, increase, and then go up like that. And that's one of the pieces, yeah, you can see all of that. That's one of the pieces of the graph of y equals tangent x. But notice it repeats the same pattern, right? We know that the next entry in the table, I think I'm going to put that in, and it's going to be 3 pi over 2 in D and E. Okay, so I know there's going to be another vertical asymptote eventually, but in between those, I'm going to repeat that same pattern. I'm going from a vertical asymptote to negative 1 to 0 to 1 to D and E. Okay, so I'm approaching a new vertical asymptote. So what I need to do is I kind of need to eyeball the width between the two vertical asymptotes that I've already got and apply that to the right. Okay, so that's going to be, I'm going to make a rough draft here. All right, so that's looking pretty good to me. And it's going to repeat the same pattern. So I'm going to draw the same graph. All right, and then if I was trying to go all the way to 2 pi, well, that would just be pi over 2 more. And the width of these intervals between vertical asymptotes is equal to pi, because it went from negative pi over 2 to positive pi over 2. So what I'm saying is x equals 2 pi, well, that's kind of also like x equals 0. Okay, I'm going to think, at least in tangent, it's going to be exactly the same. So I'm going to think that the output should be 0. That's another way you could think about it. But I think it's going to be about there, and it's just going to be that portion of the graph. That was pretty bad. I think I can do a little better than that. Okay, and then, I think I'm going to also bring in a nicer graph just to show you what it's supposed to look like. Yeah, so I went and got a Desmos graph of y equals tangent x, and I think it's good for you to see, okay, the important things is it's got these vertical asymptotes. It's got these arms, and they're kind of like going up. And so for y equals regular tangent x, we're going to see the arms are increasing, they're going uphill, and the vertical asymptotes are at pi's over 2. Okay. Some odd number of pi over 2. But I think I'm going to leave that there for the graph of regular tangent x. And before we move on to graphing like transformed versions of tangent x with a new window technique, I'm going to point out to you that the period of f of x equals tangent x is going to be pi. Okay, that's going to be important for us. We need to know that. And you can see it because that's the width between the vertical asymptotes, and it's just repeating the same behavior between each vertical asymptote. Or you could say it's the width between the zeros, or between the places where the output is 1. I think it's pretty self-evident that the period of this thing is pi. It's repetitive, and it repeats at intervals of pi. Now, the vertical asymptotes of f of x equals tangent x are going to occur at x equals pi over 2 plus pi times n, where n is an integer. And that'll be because, right, I'm going to, really, one of them is pi over 2, and it repeats every pi. The period is pi. So I'm going to say pi over 2 plus pi times n, where n is an integer. And the reason why these are the vertical asymptotes is because these are the zeros of cosine of x. Pardon me, I kind of lost my place a little bit. But the reason I've got here is because tangent is sine over cosine, and x equals pi over 2 plus pi n are zeros of cosine of x. Right up at the top, that's pi over 2. And then we would add pi to go all the way to the bottom. That'd be 3 pi over 2. And if we keep adding pi, we'll either be at the top or the bottom. Okay, so these are the zeros of cosine, so these are the vertical asymptotes of tangent. All right, now we're just going to do a little bit of window pane graphing. Okay, so this one's going to be a little bit different from sine and cosine, because in sine and cosine with this standard like 2x4 grid here, we were sketching one period of sine or cosine in your mind. Notice here it's asking for 2 periods. Okay, so what I'm going to do is I think I'm going to show you me graphing regular tangent x on the standard window. All right, so to quickly recap what we saw last time and put it on the standard window pane, we saw that x equals 0 was kind of the center of one of the periods. And so I'm going to put that in the center of my diagram here. And tangent of 0 was 0. And then we had pi over 2 and negative pi over 2 were vertical asymptotes. So I'm going to kind of put in a vertical asymptote right here and there. Okay, there. And then, as far as the actual scale goes, we're not too concerned about that because, who's to say what one's going to be? Okay, I don't like that. It's supposed to change concavity here at x equals 0. So I'm going to draw it in 2 pieces just to make sure I get the concavity right. Okay, so that's one of the pieces. Okay, both, and maybe I'll go in and label these asymptotes. That's pi over 2, and that's negative pi over 2 there. This would be a whole pi, this would be negative 1 pi. All right. And then, okay, we can label the midline, okay, because that's going to be the vertical shift factor, but we're not going to label anything else on the vertical axis. And then, just repeats the same pattern. So down here, it's going to come from that vertical asymptote, and it's going to increase up towards another 0 here. And then over here, it was 0, and it was increasing towards that vertical asymptote. So that's kind of going to be what the standard window pane graph of y equals positive tangent x is going to look like. Okay, so if we're asked to sketch 2 periods of the graph of the function, I'm just going to and we know it's a positive tangent, I'm just going to draw in the same kind of skeleton, drawing in, maybe I should leave room for a label there, but I'm going to draw in the vertical asymptotes through there. Okay, and then I'm going to label the center with my phase shift. So the phase shift is negative 5, or maybe I'll just kind of do this like I've been doing the sine and cosines. Now, if I was going to do that, I'd start with the midline, and that would be negative 6 in this case. Right, so I'm going to label that there. That's y equals negative 6. And then I'm going to say, all right, well, I'm dealing with a positive tangent, so it's going to come from above, come from below. Oh, goodness. Yeah, and that's why I should be doing these in 2 pieces. Okay, and then we'll do the other piece coming from down here. And because it's not supposed to be, hold on, let me make sure about that. Yeah, it's not supposed to be flat at these zeros. It's supposed to have a slope of 1 for reasons that you will see in calculus next year. But yeah, for now we're going to say, all right, that's going to be kind of my skeleton graph. And now all I have to do is figure out kind of the period. And you know, because I already have the phase shift. Determined that was -5. Okay, that was too slanted. That's better. So that's the phase shift. And now, remember, with sine and cosine, we would take that 4. We'd say, all right, that's b. b equals 4, and period was equal to 2 pi over b for sine and cosine, for sinusoidal functions. But for tangent, the period's pi. So in this case, it'll be period equals pi divided by b, which is going to give me period equals pi divided by 4 when I plug in b equals 4. All right, so I obviously wasn't thinking about this. This is a pretty bad example here, but I'm not gonna go like change it or anything or re-record the video. That's definitely not what we're gonna do. We're gonna say, okay, this is over here. This is -5. So if the period is pi over 4 and the width between the two vertical asymptotes is 1 full period, then that means that each square is going to be pi over 8. Okay, so I'm just gonna call this -5 plus pi over 8. Because I'd been I think I'd had somebody asking me what happens if this came up, and this is all you can do. Besides maybe figuring out what that is as a decimal number, but that doesn't really give you any better knowledge. I would call that -5 plus pi over 4, -5 minus pi over 8. I guess I'm already this far in. And -5 minus pi over 4. Now, with any luck here, yeah, the numbers on the next one will be a lot better. The only other thing I could do is I could put a y-axis over here, and then an x-axis up here, right, to indicate that I'm down there in the third quadrant, because both x and y are mostly negative through here. But then, you know, even still, like, the scale of those is probably off, so we won't be needing those. All right, and then when we go in and look at y equals 3 minus tangent x, I'm going to start with midline, like always. And that's going to be y equals 3. And then I've got a negative tangent x, so I'm going to still come with the same vertical asymptotes. Okay, I guess you can't see any of those, but yeah, there we go. Same vertical asymptotes right there on the second and fourth, or between the first and second and between the third and fourth, I guess that's what I'm saying. Okay, no phase shift, so I'm going to start in the middle at x equals 0. Need to do a little bit of work to figure out what the period is going to be. Period equals pi divided by b, which is now pi, so that's going to be 1. Okay, so the entire width of the interval between the dotted lines is going to be 1, meaning that each square is 0.5. That makes a lot of sense. If I plug in 0.5 and a tangent of pi x, I will be taking the tangent of pi over 2, which is what caused us to have a vertical asymptote in the first place. So I have -1 here and +1 there. I kind of forgot to draw the actual graph, but you know, I think that's like that. And then, okay, it's increasing up here, and it's also increasing down there. Okay, so it's coming from below and going up. And okay, not the best sketch ever, but it's certainly good enough. If we wanted to draw in a y-axis on this one, put part of it there, other part of it here. And then an x-axis would be somewhere, I don't know, maybe about there. And that's how we're going to graph functions related to y equals tangent x. Okay, secant, cosecant, cotangent, we'll graph those in a later unit, right? We're definitely going to graph those in this class. We just figured that the most important by far are sine, cosine, and tangent. Even tangent, I don't know. I don't know if that's going to be the most important. But we saw a lot of questions in AP Classroom related to that. The other three, not as many. And I am realizing I just caught it just in time. There's something wrong with this picture. What is wrong with this picture? Maybe you've been sitting there all the time like, is he going to realize, or is he just going to post this video like with the wrong graph? Okay, it was a negative tangent x. Okay, and so I think I made a very similar error when I recorded the solutions to the homework. Okay, y equals regular tangent x is always increasing. So y equals negative tangent x should always be decreasing. And then, okay, well, that kind of just tried to snap to some sort of smart curve. It thought it knew what I was doing, and obviously didn't. And then I'm going to come back down here for one more. Okay, and that is the accurate graph of g of x, which is negative tangent. Okay, so, you know, with these negative tangents, this is how we're going to graph them using the window technique. I think past this, you need to just work on your own and then maybe check your answer against the homework solution video. That's going to be all for this video. Thanks for watching.